All right, folks. So I wanted to make a video for you doing another example from section 1.8. So this is a section that we learned about linear transformations and how to show something's a linear transformation. But I thought it'd be really useful to have one more example actually showing, right, that a given transformation is linear. So this is from your book, section 1.8, number 35. We're given a transformation T from R3 to R3. And it has the following definition. So T of x1, x2, x3. So this is my initial vector, right? Again, we're writing it as a row, but really we're thinking about this as a column vector. That's fine. The output of that vector is x1, x2 minus x3. Okay. And our goal is to show that this transformation is a linear transformation. So just for intuition, what is this transformation doing? Well, it's taking any arbitrary vector and then outputting the same vector, except the third component is reflected, right? It's the negative of the input. And so if I have my x1, x2, x3 coming out of the board space, so what this transformation is doing is, well, the blackboard is the x1, x2 plane, x3 is pointing out towards us. And if I take any input vector, say it points out here where my hand is, the image of this under the transformation is reflected through the blackboard, right, on the other side of the blackboard. So every point gets reflected to the other side, okay, sort of equally distanced. Okay. So this is a reflection operator. Okay, so again, my goal is to show that this is a linear transformation. How am I going to do this? Well, I'm going to use the theorem that we proved in class, which was that if I can show that T of Cu plus dV equals Ct of U plus dt of V for all scalars C and D, all vectors U and V, then T would be a linear transformation. So what I need to do is really check that this equation holds. So let's try it out. We'll start by letting C and D real numbers, and let's let U and V be arbitrary vectors from R3. So like we did in class, when we start on the left-hand side and say, well, T of Cu plus dV equals. Now I need to start manipulating things and figure out how to get my way towards the right-hand side of this equation. In order to do that, maybe you look at this transformation and what's given as the formula for it, and you say, well, it's not that easy to know how to apply this in this setting. And why don't we know how to apply this? Well, U and V right now are sort of just arbitrary vectors that are kind of just, ambiguously defined in some way, right? I mean, I don't really know what the components are, and yet the function itself is defined in terms of the components. So how do I get around this? Well, what I should do is really write down what is U, right? U is an arbitrary vector, so I know it has three components. Let me call them U1, U2, U3. V has three components, right? Let me just call them V1, V2, V3. Now it doesn't look so ambiguous, so mysterious. I can actually say what these vectors are. It'll be easier to apply this formula, right? So let me go ahead and do that. So T of, let me call it C times U1, U2, U3, right? Just writing out that arbitrary vector U as its components, plus D times V1, V2, V3. And because I want to apply the transformation, let me combine all of this into one big vector. So this is T of, so CU1 plus DV1, CU2 plus DV2, CU3 plus DV3. Right? So what I've done is rewritten U and V, these arbitrary vectors, as their components, and then collect them together into one big vector. Now, T is being applied to this 3 vector, and I have a formula of what the output should be, right? The output of this function should be CU1 plus DV1, CU2 plus DV2, and the last component should be the same quantity, but with a negative sign in front. So negative Cu3 plus DV3. Awesome. So now I've gotten some progress. Remember, my goal is to sort of work my way to this right-hand side. It looks like what I want to do is split this vector now up into its pieces again. So let me first distribute the minus sign. I get CU1 plus DV1, CU2 plus DV2. My third row is going to be minus CU3 minus DV3. Let me now split this vector up into two pieces and factor out the common factors of C and D from each of those vectors. So the first vector I'm going to have, right, is going to be C times U1, U2 minus U3 plus D times that second vector, but remaining V1, V2 minus V3. This is great. Why? Look at the vectors I ended up with. U1, U2, U3 is not just a random vector. Well, U1, U2 minus U3, right? This is what happens if I plug in U, the vector U, into the function T, right? I'm going to get U1, U2 minus U3, right? So that's exactly what I'm looking at here. And so this first vector is C times the image of U. The second vector is exactly D times T of V, right? The image of V, right? Because I took V1, V2, V3 and plugged it in, I would get V1, V2 minus V3. So look what we ended up with. CT of U plus DT of V. It's exactly the right-hand side I was looking for. We've just proved that this function is linear, and therefore we're done. All right, so hopefully this is a good example to help you see, again, what the general philosophy is of how to prove something is linear. If you have questions, please let me know. We can come talk about it. All right,